Steam locomotives killed people. Not just in crashes, but through design decisions so dangerous that governments outlawed them entirely. From cabs that roasted engineers alive to boilers that could not generate enough steam, these prototypes pushed engineering straight into catastrophe. Here are 20 old locomotive prototypes banned for being too dangerous. The Reed Ramsey turbine electric arrived in 1910 as the world's first attempt to marry steam turbines to railway traction. Built by the North British Locomotive Company, this bizarre machine promised to revolutionize rail travel by eliminating the hammering forces of reciprocating pistons. The theory was elegant. Steam would spin a turbine, then drive an electrical generator, and that would power traction motors. Smooth, quiet, efficient. The reality was a mechanical nightmare. The electrical transmission system could not handle the stresses of railway operation. Bearings failed. Generators overheated. The condensing system, essential for turbine efficiency, proved hopelessly inadequate in the confined spaces of a locomotive. Test runs revealed a machine that consumed coal at terrifying rates while producing barely adequate power. Mechanics spent more time repairing it than running it. Within months, the North British Locomotive Company quietly rebuilt the entire locomotive with conventional direct-drive turbines, hoping to salvage something from the disaster. That attempt failed too. The rebuilt machine limped through a handful of tests before being abandoned entirely due to persistent mechanical failures that made it utterly useless for regular service. In 1933, Italian state railways decided to transform a perfectly good Class 6 8.5 locomotive into a steam turbine experiment. Engineers removed the reliable piston engine and installed a steam turbine in its place, leaving everything else completely unchanged. The locomotive still looked like a standard 2/6/2 wheel arrangement, but now it had turbine gearing where pistons once lived. The results were catastrophic. Performance plummeted to levels well below the original piston-driven locomotive. The turbine simply could not deliver power efficiently across the speed ranges that railway operation demanded. Starting from rest required enormous steam consumption. Maintaining speed on grades proved nearly impossible. The boiler, designed for a reciprocating engine's intermittent steam demand, could not keep up with the turbine's constant appetite. Within months, the turbine mechanism literally broke apart during testing. Metal fragments scattered through the machinery as stressed components gave way. Italian engineers did not bother rebuilding the experiment. They simply refitted the locomotive with a conventional piston engine in 1936 and pretended the whole turbine episode never happened. The failed conversion stood as proof that bolting new technology onto old designs rarely ends well. Ross Winans built his first camel locomotives for the Baltimore and Ohio Railroad starting in 1848, and from the beginning, crews knew something was terribly wrong. Winans wanted maximum weight over the driving wheels for better traction, so he mounted the engineer's cab on top of the boiler, roughly in the middle of the locomotive. The fireman worked alone on a platform at the rear, completely exposed to weather and separated from the engineer by an entire roaring boiler. Communication between crew members became nearly impossible above the noise. Engineers perched directly above the whirling side rods and main rods, with nothing but thin cab walls between them and disaster. If a rod broke, the resulting metal fragments would tear directly through the cab. Railroad workers called these locomotives dangerous long before safety regulators existed. The crew separation meant that emergency responses were delayed or impossible. An engineer suffering heat stroke might collapse while the oblivious fireman continued stoking coal. Despite these dangers, Winans built hundreds of camels, prioritizing fuel savings over human safety in an era when worker deaths were considered acceptable business expenses. The Pennsylvania Railroad's engineering department in the 1930s sketched designs for what would have been the most ambitious articulated locomotive ever conceived. The proposed V1 class would have featured 4 complete engine units, essentially quadrupling the triplex concept that had already proven problematic on the Erie and Virginian railroads. Internal documents show engineers planning for over 200,000 pounds of tractive effort. numbers that existed only in calculations. The design never progressed beyond paper because even preliminary analysis revealed insurmountable problems. No boiler then conceivable could generate enough steam for 4 sets of cylinders operating simultaneously. The locomotive would have exhausted its steam reserves within seconds of starting, leaving a £250,000 machine stranded on the main line. Thermal stress calculations showed boiler plates warping under impossible demands. Frame structures could not be built strong enough to contain the articulation points without exceeding weight limits on every bridge in the system. Pennsylvania railroad engineers quietly shelved the proposal, recognizing that ambition had outpaced physics. Sometimes the most dangerous prototypes are the ones never built. The Chesapeake and Ohio M1 class arrived in 1947, looking like something from science fiction. 3 of these 106-foot monsters were built by Baldwin-Westinghouse to prove that steam could compete with diesel on premier passenger runs. The coal-fired boiler fed steam to turbines which powered electric traction motors, an elegant hybrid that promised the best of both worlds. Instead, it delivered the worst of everything. Coal dust proved to be the M1's nemesis. The fine particles infiltrated the traction motors constantly, grinding away at windings and commutators. Water from the condensing system followed the dust, turning coal residue into an abrasive slurry that destroyed electrical components. Crews reported motors burning out on nearly every run. The boiler controls proved temperamental, requiring constant adjustment to maintain proper steam pressure. The locomotives could not complete a single journey from Washington to Cincinnati without suffering some kind of failure. After spending millions on development, the C&O operated their M1s for barely a year before giving up. All 3 were scrapped in 1950, having proven that coal and electrical equipment simply cannot coexist in the same machine. The Virginian Railway's Class XA was the only 28884 ever built, a triplex so ambitious it bordered on engineering fantasy. Baldwin delivered number 700 in 1916, promising a locomotive capable of moving coal trains up steep Virginia grades without helper engines. The reality proved humiliating. This massive machine could barely sustain 5 miles per hour. The boiler, despite being larger than anything previously attempted, simply could not generate enough steam for 6 enormous cylinders operating simultaneously. Crews watched pressure gauges drop towards 0 within moments of opening the throttle. The rear engine set mounted under the tender lost traction as coal and water were consumed. Starting fully loaded, the tender provided excellent adhesion. Halfway up a grade with supplies depleted, the rear wheels would spin uselessly while the front engine sets strained to compensate. Baldwin engineers traveled to Virginia hoping to solve the problems, but achieved nothing. After less than 5 years of frustrating service, the Virginian returned the locomotive to Baldwin, who cut it apart and rebuilt it as 2 separate conventional locomotives. Even the railroad's official designation XA acknowledged the experimental nature. The X stood for failure. Baldwin built the first triplex for the Erie Railroad in 1914, naming it the Matt H. Shea, after a beloved company engineer. The concept seemed logical. Put 3 complete engine sets on 1 locomotive frame, achieve unprecedented tractive effort, and eliminate the need for multiple helper engines on steep grades. The reality proved that some problems cannot be solved by simply adding more cylinders. The Matt H. Shea generated 160,000 pounds of tractive effort, more than any steam locomotive before or since. This massive force immediately created new problems. Couplers snapped. Car frames twisted. Drawbars pulled out of freight cars like corks from bottles. One early test run managed just 17 miles before the locomotive literally pulled a coupler clean out of a coal car. The boiler could not sustain full power for more than a few minutes. An Erie fireman later wrote that standing behind the fire door was the best place to cool off on a summer day. The locomotives consumed coal and water faster than crews could shovel and pump. 3 triplexes were built, all relegated to pusher service on short grades. By 1929, all had been scrapped, having proven that maximum power means nothing when your boiler runs dry. The LNER W1 number 10,000 earned its Hush-Hush nickname because of the secrecy surrounding its development, but the locomotive's problems proved impossible to hide. Nigel Gresley designed it with a water tube boiler operating at 450 pounds per square inch, more than double the pressure of conventional locomotives. The theory promised dramatically improved efficiency. Marine engineers had proven high-pressure water tube boilers worked brilliantly in ships, but railway operation proved far less forgiving. The boiler leaked constantly. Air found its way into the casing through joints that could never be properly sealed. Pressure dropped unpredictably, leaving crews struggling to maintain power on demanding runs. Steaming proved so poor that the locomotive could not match the performance of standard Gresley Pacifics despite its advanced technology. The compound expansion system required constant adjustment. Maintenance crews spent more time repairing the W1 than it spent in actual service. After 7 frustrating years, the LNER admitted defeat and rebuilt the entire locomotive with a conventional boiler in 1936, erasing Gresley's ambitious experiment and proving that shipboard success does not translate to railway tracks. The Pennsylvania Railroad S2 was supposed to prove that steam could outperform diesel at its own game. Baldwin and Westinghouse delivered this 686 direct drive turbine locomotive in 1944, and at high speeds, it performed magnificently. Above 40 miles per hour, the turbine consumed less fuel than conventional locomotives while delivering smooth, silent power. The problem was everything else. Below 40 miles per hour, the S2 became an engineering disaster. Turbines require high rotational speeds to operate efficiently, and gearing that worked beautifully at highway velocities proved catastrophic at yard speeds. Fuel consumption at low speeds exceeded 3 times normal, emptying coal bunkers and water tanks at alarming rates. Starting a train from rest meant burning through reserves that should have lasted the entire run. Railway operation involves constant speed changes. Trains accelerate from stations, slow for curves, stop for signals, and crawl through yards. The S2 excelled at exactly one thing, sustained high-speed running, and failed at everything else. By 1949, severe turbine damage ended the experiment. The locomotive was scrapped in 1952, having logged just 103,000 miles before proving turbines belong in power plants, not on rails. Norfolk and Western's Jawn earned its nickname from the legendary steel driving man who raced against a machine and won, only to die from the effort. The locomotive's fate proved grimly appropriate. Built by Baldwin Westinghouse in 1954, this steam turbine electric stretched 161 feet from coupler to coupler, making it the longest steam locomotive ever constructed. The boiler operated at 600 pounds per square inch, nearly double conventional pressure. The design promised to preserve coal hauling jobs in Norfolk and Western's Appalachian territory by proving steam could match diesel efficiency. Instead, it demonstrated everything wrong with late-era steam technology. Coal dust infiltrated the electrical equipment constantly, destroying traction motors and generators. The locomotive's extreme length meant it could not use any turntable on the Norfolk and Western system. The complex controls confused even experienced engineers, leading to mistakes. The water tube boiler required specialized maintenance that most crews could not perform. Performance ran 15% below the conventional Class A locomotives it was supposed to replace. Norfolk and Western scrapped it in 1958, the last desperate gasp of steam dying 4 years after birth. The Pennsylvania Railroad's T1 duplex looked magnificent and ran like a nightmare. 52 of these streamlined 4444 locomotives were built between 1942 and 1946, designed by Raymond Loewy to be the fastest passenger power in America. They achieved that goal, reportedly touching 140 miles per hour on test runs. But the T1s concealed a fatal flaw that made them nearly uncontrollable. The divided drive arrangement placed 2 sets of driving wheels on a rigid frame, each powered by its own cylinders. This made the T1 extraordinarily prone to wheel slip, violent wheel slip that occurred without warning at any speed. Engineers reported front drivers spinning wildly, while rear drivers gripped normally, sending shudders through the locomotive. The poppet valves, chosen for quick steam admission, made problems worse by delivering power in sudden bursts. Training programs never materialized. Crews accustomed to conventional Pacifics found themselves wrestling machines that responded to throttle inputs in unexpected ways. Wheel slip damaged valve gear, which caused more slip. By 1948, the Pennsylvania Railroad had begun replacing their revolutionary T1s with diesel locomotives. Every single locomotive was scrapped. None were preserved. The entire fleet was erased from existence. The London, Midland and Scottish Railway locomotive number 6399, Fury, represented Britain's most ambitious attempt at high-pressure steam, and it ended in death. Built in 1929, with a revolutionary Schmidt-Henschel boiler, Fury operated at pressures ranging from 900 to 1,800 pounds per square inch in its ultra-high pressure circuit, nearly 10 times conventional boiler pressure. The theory promised dramatic fuel savings through thermodynamic efficiency. The reality arrived on February 10, 1930. During a test run from Glasgow to Carstairs, one of the ultra-high pressure tubes burst catastrophically. Scalding steam and boiling water erupted through the cab, ejecting burning coals from the firebox. Lewis Schofield, an engineer from the superheater company who was riding on the footplate to monitor performance, suffered horrific burns. He died the following day. The driver and fireman escaped with lesser injuries only because they stood further from the rupture point. Investigators at Sheffield University examined the burst tube but never determined a definitive cause. The railway repaired Fury and continued testing, but performance never justified the complexity. In 1935, the railroad admitted defeat and rebuilt the locomotive with a conventional boiler. The Midland Railway's Paget locomotive number 2299 was so secret that only one official photograph exists, and its problems explain why the railway wanted it forgotten. Built in 1908 to Cecil Paget's personal design, this bizarre 262 wheel arrangement featured 8 uniflow cylinders arranged in 2 groups between the driving axles, all controlled by rotary sleeve valves. The concept promised smooth power delivery without the hammering forces of conventional valve gear. The execution proved catastrophic. The bronze sleeves operating inside cast iron steam chests could not handle thermal expansion. As the engine heated up, different metals expanded at different rates, causing the sleeves to seize solid. In 1912, one of the rotary valves locked completely during a test run, stranding the locomotive on the main line for 7 hours, while crews struggled to free the mechanism. The constant leakage past the 192 piston rings required for the sleeve valve system wasted steam continuously. Crews described the machine as impossible to keep running. The Midland stored the locomotive at Derby Works, where it sat untouched until 1918. While Cecil Paget commanded railway troops in France, his creation was quietly cut apart and scrapped. The Delaware and Hudson Railway spent a decade chasing the dream of high-pressure steam, building 4 experimental locomotives between 1924 and 1933 that pushed boiler technology to its absolute limits. The first, number 1400 Horatio Allen, operated at 350 pounds per square inch in 1924. Each successor increased the pressure. Number 1401, John B. Jervis, reached 400 pounds per square inch in 1927. Number 1402, James Archibald hit 500 pounds per square inch in 1930. The final experiment, number 1403 LF Laurie, also operated at 500 pounds per square inch in 1933. These Muhlfeld water tube boilers achieved remarkable thermal efficiency on paper. Number 1403 was possibly the most thermally efficient steam locomotive ever built. But efficiency meant nothing when the locomotives could not maintain speed. All 4 struggled to exceed 5 miles per hour under load. The complex compound expansion systems required constant adjustment. Specialized maintenance meant that only crews at the home shops could properly service them. Road failures stranded trains regularly, requiring conventional locomotives to rescue the experimental machines. By the late 1930s, all four had been scrapped or rebuilt with conventional boilers. Delaware and Hudson proved that theoretical efficiency cannot overcome practical unreliability. Oliver Bulleid's leader class looked like a diesel-like locomotive, but it contained a steam engine designed to torture its crew. Built at Brighton Works, starting in 1946, this double-ended 0660 was supposed to modernize steam traction by enclosing all working parts and allowing operation from either end. The reality created working conditions so brutal that firemen refused to operate it. The central fireman's compartment sat directly beside the boiler with minimal ventilation. Heat built to unbearable levels. More than one fireman collapsed from heat exhaustion during test runs. Flames from the firebox occasionally entered the cab during high-output running, adding the threat of burns to the misery. The sleeve valves that powered the chain-driven bogies seized repeatedly. Firebricks lining the firebox collapsed into the fire, then their cast-iron replacements melted in the intense heat. Crank axles broke twice during testing, each time stranding the locomotive. British Railways inherited the project after nationalisation in 1948 and poured money into solving the problems. By 1951, they gave up entirely. All 5 leader locomotives were scrapped. The project abandoned as proof that diesel-like appearance cannot hide steam-era suffering. Chesapeake and Ohio, locomotive number 3020, a Class T1210-4, killed 3 men on May 12, 1948, in an explosion that demonstrated how quickly a perfectly maintained locomotive could become a deadly bomb. The disaster occurred near Chillicothe, Ohio, during what should have been routine freight operations. The water level in the boiler dropped below the crown sheet, the steel plate that forms the top of the firebox. Without water to absorb heat, that steel began to glow cherry red. Temperatures climbed past 1,200 degrees, the point where steel loses structural strength. 200 pounds of pressure inside the boiler found weakness in the softened metal. Engineer W.R. Terry, fireman T.R. Lauter, and front brakeman W.C. Bush died instantly when the crown sheet failed. The physics were merciless. Some 2,500 gallons of superheated water flashed to steam in a fraction of a second, expanding to 4 million gallons of vapor. The boiler launched upward, tearing free from the locomotive frame. Crown sheet failures had killed locomotive crews since the beginning of steam railroading, and they continued killing even on modern equipment. The Chesapeake and Ohio retired all T1 class locomotives by 1953. The morning of March 18, 1912, began normally at San Antonio's Galveston, Harrisburg, and San Antonio railway yards. Locomotive number 704 sat building steam for its day's work. At 8:55 a.m., the boiler exploded with force that stunned the entire city. The main boiler section, weighing 16,000 pounds, rocketed 1,200 feet through the air before crashing to earth. The boiler head, a 1,250-pound chunk of steel, flew an equal distance in the opposite direction. Buildings within a 100-foot radius collapsed from the blast wave. Engineer Walter Jourdain and painter José Fuentes died instantly, their bodies barely identifiable in the wreckage. The investigation revealed a cascade of failures. Someone had tightened the safety valves to increase pressure beyond safe limits. The steam gauge showed false readings, telling the crew everything was normal when pressure had climbed to catastrophic levels. The boiler itself contained substandard material, weakened by years of service. An inexperienced employee had been left alone with a machine he did not fully understand. Every protection designed to prevent explosion had failed simultaneously. The disaster rewrote safety regulations across American railroads. Steam locomotive 1278 exploded on June 16, 1995, near Gardners, Pennsylvania, proving that crown sheet failures did not end with the steam era. The locomotive, built in 1920, had operated for decades as a tourist attraction on the Gettysburg Railroad. That summer morning, the water level dropped below the crown sheet, while the locomotive hauled a passenger excursion through the Pennsylvania countryside. The sequence that followed had remained unchanged since the 1830s. Steel overheated, strength vanished, pressure found weakness. The crown sheet blew inward, unleashing superheated steam through the firebox and into the cab. The engineer suffered third-degree burns, over 65% of his body. 2 firemen received serious burns, requiring extensive hospitalization. Passengers in the trailing coaches heard the explosion and felt the train lurch to a stop. The National Transportation Safety Board investigation found inadequate training, improper maintenance procedures, and lack of specialized knowledge among the crew. Heritage railroads across America scrambled to review their own procedures. The Gettysburg explosion demonstrated that historical equipment requires more than enthusiasm to operate safely. It demands expertise. Many tourist operations lacked. East Germany's last locomotive boiler explosion occurred at Bitterfeld Station on September 9, 1977, when Deutsche Reichsbahn Locomotive 011516 demonstrated that even modern safety systems can fail. The Class 01 Pacific had operated behind schedule that morning, and the crew faced pressure to make up time. As the locomotive waited at the platform, the fusible plugs that should have melted to warn of low water failed to function. These lead alloy plugs were designed to melt at temperatures below the danger point, releasing steam to alert the crew. Years of service had compromised their reliability. Without warning, the boiler detonated. The force overturned the locomotive lengthwise, the barrel scraping along the station roof before crashing back to the platform. The explosion sent debris across the crowded station. Remarkably, no passengers died, though crew members suffered severe injuries. Deutsche Reichsbahn implemented new regulations requiring regular fusible plug replacement on all remaining steam locomotives. The Bitterfeld disaster marked the end of assumptions that routine operations on proven designs carried acceptable risk. The best friend of Charleston holds a grim distinction in American railroad history. On June 17, 1831, it became the first locomotive in the United States to suffer a boiler explosion, establishing a pattern of death that would continue for over a century. The locomotive had operated successfully since Christmas Day, 1830, running passenger service on the South Carolina Canal and Railroad. The explosion resulted from the simplest possible cause. The fireman, annoyed by the constant hissing of steam escaping from the safety valve, decided to silence it. One account says he tied the valve shut. Another claims he placed a wooden board on the valve and sat on it. Either way, he disabled the one mechanism designed to prevent catastrophic overpressure. With no escape route, steam pressure climbed until the boiler could no longer contain it. The resulting explosion hurled metal fragments across a wide area and killed the fireman instantly. Engineer Nicholas Darrell survived with severe injuries. The railroad salvaged what remained and rebuilt the locomotive as the Phoenix, but the lesson was clear. Steam power demanded respect for safety mechanisms. Generations of railroad workers would die learning that same lesson again and again. And that's all, folks. These were 20 locomotive prototypes, so dangerous they were banned, scrapped, or abandoned before killing anyone else. Don't forget to subscribe for more railroad history. Here is another video I have specially selected for you. See you next time.